Hi everyone, I'm Professor Bergasser, and in this video we're going to be talking about a special case study on pulleys. Pulleys are our second of our simple machines, which also include inclined planes and levers. And they're seen very often in the rigging of boats where you have to pull up sails that may be very heavy, and also in heavy lift cranes, even the cranes that build buildings. They're a simple machine. They're based mostly, basically a wheel and a rope that's wrapped around that wheel. There may be multiple wheels and multiple ropes, so we'll build up that complexity as we go along. And the whole purpose is to be able to lift something that otherwise would be very difficult to lift, either because of the angle in which you're lifting or even just the weight of the object that you're trying to lift. So we're going to start with our simple case of just a single pulley wheel and look at quantifying something called mechanical advantage. And that's essentially the ratio of how much force you have to apply compared to how much weight that you're trying to lift. And so we can actually come up with a numerical value of just the ratio of those two numbers, the weight over the force applied. So we can ask that for this very simple pulley wheel, and we can look at some predictions on what we think might happen as a result of this particular setup. So if you've ever used a pulley wheel at all, you could probably recognize that as I'm pulling down on one side of the rope, I could pull down, which lifts the weight up. And so certainly one of the predictions is that the direction of the force is opposite the acceleration of the weight. All right, so if I pull it hard enough so that the weight will go up, then the weight will go up, but I'm pulling down, so it's the opposite direction. And we certainly need to have a force that's greater than mass times g for acceleration up. And whether or not we have a mechanical advantage, I think that's something that's going to come out as we write down the equations. Okay, so let's start with our regular protocol of drawing the force diagram. In this case, we're going to look at two different points. We're going to look at the mass, and we're also going to look at the point in which we're actually pulling down on this rope, this sort of connection point. So let's go ahead and draw those two. The point which we pull is a pretty simple drawing, right? It's just a point. We are pulling down with a force F, and we'll assume that there's a tension acting at this point T. And since we're just considering just a point on the rope, this point doesn't have any mass, so we don't have to write anything like the weight of that piece of rope, at least in this case of this problem. And that's all the force we have on that one point. Let's look at the other side, which is where the mass is suspended. Of course, this object has a mass, so it will have a weight component to it, m times g. And it's connected by the rope for a tension force going upward, and so we can draw that tension force as well. And that's all the forces that we need to worry about for this problem. Now, this turns out to be very simple. We've got just two objects, all the forces along one dimension in each case, which I'm going to label as the y direction. I'm going to point y going upward. And so we really just need to write down two equations to describe the equations of motion for this object as it moves. So let's start with our first object here, our point 1, so that's 1 and 2. In this case, we're just looking at the y components of force. That's equal to the tension minus the applied force. And that would normally be equal to the mass of this point times its acceleration. But I've already said that I'm looking at a point that's so small it's just a massless little connection of the ring. So this is equal to 0. And so this immediately tells us that whatever force I'm applying, that's equal to the tension in the rope throughout the system. All right, so that's a very convenient way of figuring out what that tension is. It's simply the force that's applying at one end of the rope. Let's look at the other object and its sum of forces. All right, that's fairly simple to write. It's T minus mg, and that's equal to the mass times its acceleration. And since I know T is the force applied, this is just force minus mg. All right, and so now there's a couple of questions we can ask. Let's say we want to look at the case where the acceleration is greater than 0, which is the case where the block moves up. Well, the only case for that to happen is when F minus mg is greater than 0, and that means that the force is greater than mg, which is exactly the prediction I made for the case where we'd have to have a force greater than the weight in order to accelerate this object up. And similarly, if I wanted to look at the case where the acceleration is down, or this object is falling down, that's force minus mg is less than 0. So that's a case where the force is less than the weight. So if I don't apply a force that's sufficient to cover the weight, then this object will start to fall down, which means that the mechanical advantage is going to be basically just 1, right? It's only the case where F equals mg that the acceleration is equal to 0. And so when I apply a force that's equal to the weight, that's the only case where I can actually hold up this weight. So this means that the mechanical advantage, ma, is equal to 1. So the simple pulley wheel doesn't provide enough mechanical advantage, or really any mechanical advantage, although it does allow us to change the direction in which we apply the force. So as opposed to pulling this weight up, which may be hard to do structurally, we can flip around and just pull the weight down, and that provides us a way of lifting something or lowering something down from a convenient perspective. So pulley systems don't start to convey mechanical advantage until you allow the pulley wheels themselves to move with the object. And the most simple setup for this is something called the gun tackle, where you have one fixed pulley wheel and then a pulley wheel that's connected to the mass, and these two are strung together such that as I raise or lower this string, the second pulley will actually move with the mass. So we'll see in this sort of calculations how that actually conveys some mechanical advantage when we're pulling objects up. And by the way, this, as I said, this is called a gun tackle, and it's commonly used when we're loading things onto boats, for example. All right, so let's think of some predictions for this motion. I've already said that this is going to convey some mechanical advantage, and so we can think of that we're going to have the case where if we have a force that's less than the weight, that's still going to hold it up, or hold up the mass. All right? And that's kind of the thing we're actually looking for in this case, in this calculation. We'll also notice that as we raise or lower the string, if I say pull the string by, let's say that's 1 meter in length, then we have to have another meter in length in this part of the string diagram coming back, but in fact that's divided into 2 separate segments. And so the other prediction about this is that while it may convey a mechanical advantage, we're also going to get less pull length from the mass side. Okay, so as I pull, say, a meter on this end of the string, the mass should only go by half of that, because that string length is being shared across that pulley. All right, so in order to sort of calculate what the exact mechanical advantage of the system is, let's go ahead and draw our force diagrams. We have 3 points that we want to consider. The point here where we're actually pulling, the pulley itself that's moving, and our mass, which is the thing we're actually interested in lifting up. So let's draw 3 force diagrams for each of these. For the point that we're pulling, we've got our usual tension force pointing up and our pull force pointing down. And in fact, nothing has changed for this particular point, so we're still going to get the case where, because this little piece is essentially massless, that the tension through the rope is still equal to the force that's applied. That's an important thing that stays constant for all of these pulley problems. Looking at the pulley wheel, actually, let's take a look at the mass first. So we're going to draw that over here. That hasn't changed very much either. We have our, oops, wrong color. We have our weight pulling this down, mg. And now we have a different connector between the mass and the second pulley wheel. So I'm actually going to call that TP for the tension in the wire that's connecting the mass to the second pulley wheel. And finally, let's draw in our force diagram for our pulley wheel. I haven't mentioned whether the pulley wheel has a mass or not, so let me go ahead and put in some unknown mass for the pulley wheel for this, in which case that we have to write down the weight of that pulley wheel, which is mp times g, and then all of the connection parts to that wheel. So it's connected to the string that's connected to the mass, and that's going to pull down as well. And it's also connected to the string that's running around both pulleys. And so at both of those connection points, you're going to get a tension force that's pulling up on the pulley wheel. All right. Same force on both ends because they're conveyed by the same string. And as we'll see, that's going to be the point where we get some actual mechanical advantage. So let's go ahead and draw our coordinate system as before. It's just a one-dimensional coordinate system, although again we have now 3 different objects, so in principle you have to write 3 different equations of motion. So let's go ahead and start with our first point. That is the sum of the forces is equal to tension up minus force down. And because again I'm assuming that this is essentially massless point, we're going to set that equal to 0. So that means that force applied and the tension in the rope are exactly the same. Looking at our second object, which is the pulley wheel, we can add up the sum of the forces for that. That's going to equal to 2 times the tension, or let's actually put in our force, 2 times the force, minus TP minus MPG, right? And that's going to equal to the mass of the pulley times its acceleration, AP. And finally, we'll write the equation of motion for the mass itself. Sum of the forces is equal to the TP minus the mass times G, its weight, and that's equal to the mass's acceleration, m times a. All right, now let's take a look at our equations here. We've sort of already used equation number 1, and so what we're looking at is 2 equations with really 3 unknowns. The tension in the wire connecting the second pulley to the mass, the acceleration of the pulley, and the acceleration of the mass itself. And so 2 equations, 3 unknowns, we need another equation, we need a constraint equation. And we can get that by looking at the string connecting to the pulley to the mass. That string, if we assume doesn't stretch or shrink, is always going to have the same length. And so as I move the pulley up, the mass is just going to follow with it and vice versa. And so that gives a connection between the acceleration of the pulley and the mass, that they're going to be the same. This is the constraint, okay, of their motions. So that allows us to cancel one of those unknowns, and we can now write down these equations fairly straightforwardly. What I'm going to do is write down this equation, but I'm going to substitute in my expression for TP. So let's write that in. TP is equal to mass times acceleration plus gravity. All right, so now we can write down 2F, and I'm going to actually move these things over. So 2F equals 2P, but that's mass times A plus gravity. And I'm going to move the MPG over, and that's equal to MP times acceleration plus gravity. Or writing everything out, the net force that I'm applying is going to support the mass of the weight plus the mass of the pulley times their acceleration, their common acceleration, and their acceleration due to gravity. All right, so how do we get from this into the mechanical advantage? Well, we can look at the case where the acceleration is equal to 0. That means that the force is equal to 1/2 times the sum of the masses times g. And so if I write down our mechanical advantage, which is really the weight over the force, well, this is actually equal to, the weight is this right here. And so this is actually going to be equal to 2. And so our mechanical advantage for this 2-pulley system is 2. We're able to literally hold up twice as much weight with the same amount of force. We can also look at examples where if we want the acceleration to be greater than 0, which is the case where both the mass and the pulley rise up, that's going to be a case where the force is greater than this number, and vice versa. And often we'll look at cases where this mass is much, much more massive than the weight of the pulley, in which case we can just approximate this as the force at acceleration equals 0 is 1/2 times the weight. So I literally have to apply 1/2 of the weight in order to hold this object up. That's the great power of these pulley systems. So let's go on to an even more complex system where we have multiple pulley wheels, multiple fixed and multiple movable pulley wheels. This is the construction often known as the block and tackle system, in which you can combine several different cables together or several different pulleys together to increase your mechanical advantage. And so in reality, it might look like this, where you have one fixed pulley wheel and one movable wheel with the rope connecting them going around and around and around several times. This is more schematic, showing how you could break up this system into individual pulley wheels, some of which are fixed, some of which are movable, and this can continue on as many as we want, depending on what mechanical advantage and what limitations we actually have on the support structure for the system. So to see how we can break this down, let's just take the case of what I've drawn here, which is a 4-cable system. We'll call this a 4-fold purchase, and we can draw similar kind of force diagrams for the mass and the bottom pulley wheel. Now it's good to make a prediction on this system, and of course as we're going to complexity, the prediction should be that we'll increase the mechanical advantage and it will depend on the number of loops of cabling between them. So in some way, the mechanical advantage that we get out should depend on how many times that we string this together. All right, so let's see if we can get an insight into this by drawing our force diagrams. Let's draw a force diagram for our mass first, because that's going to be the easiest one. All right, we already know that we're going to have a weight pointing down and the tension from the pulley immediately above it pulling up. And then for that pulley wheel, oops, make sure we write the right colors here. For the pulley wheel, we've got our pulley and we've got its weight, which I haven't specified but might be present. We've got that tension force that's connected to the mass, and then we've got a whole series of tensions that are applying for every string that's wrapped around here. And in fact, there's 2 for every one, because we've got a string that comes in and comes out. Both sides are pulling the pulley wheel up. So if we have a 4-fold purchase, we're going to have on either side 4 forces, all T, and on the other side as well, all T pointing up, lots of forces pulling on this particular pulley wheel, and those are the forces that are going to hold both the pulley wheel and the mass up. We go back to our equations of motion, much the same way that we've done in the last couple examples. For the mass, we'll call that number 1 and number 2. So for number 1, the sum of the forces in the y direction are equal to the tension force between the mass and the pulley wheel minus the weight, and that's its mass times acceleration. And for the pulley wheel, we've got 8 tension forces minus our TP and minus the weight of the pulley wheel is equal to its mass times its acceleration. And we have exactly the same constraint equation as we had in the last case, where the acceleration of the mass is equal to the acceleration of the pulley wheel. And so that allows us to solve for our equations exactly the same way as we did before. And in fact, what we get out in the end, and noting of course that the tension is equal to the applied force, which is what we always get from the endpoint there, that we would get the force applied is going to equal to 1/8 times the sum of the masses of our weight and our pulley wheel times the sum of their acceleration plus their surface gravity, because of surface gravity acceleration. And again, if we have A equals 0, this is going to give me the force is 1/8 times the sum of the masses times their gravity. And if I want to compute the mechanical advantage, that's equal to the weight divided by the force, and the weight is that number right there, so this is equal to 8. So we've greatly increased the mechanical advantage. I only have to put a force equal to 1/8 of the total mass of the pulley wheel and the thing that I'm holding in order to hold this thing up without letting it fall. And as you can see, we've done 4 strings, we've got a mechanical advantage of 8. When we had 1 string, we had a mechanical advantage of 2. And so we can more generally write down that the mechanical advantage for n loops is going to be something like 2n. So by solving for a couple of cases, we're able to do a much more general rule about what the mechanical advantage is for a pulley system, a block and tackle pulley system, based on the number of loops that I string these strings around. And that provides a much more general expression for thinking about how we can increase our mechanical advantage. Now in all these cases, we've just applied the normal protocols for solving our force diagrams, drawing our forces, setting up our coordinate system, writing down the equations of motion, and solving for the unknowns. But you can see that it's generally applicable for more complicated systems. If we start simple, we can build up to things that look like very challenging problems, but in fact are just replications of the things that we've solved before.